Okay, good morning, students. Today we will discuss about the last two topics of our first unit, that is impact of technology scaling along with a technology and device innovation. So let's start our topic. First we will discuss about the effect of scaling in technology. We already know that the minimization of VLSI device is possible because of this scaling. Now, what is the mean of scaling? Which parameter is scaled by using for minimization? Which parameter is scaled for the minimization of VLSI device? Scaling means variation. So in VLSI field, for minimization, we vary the thickness of gate oxide layer. We vary the thickness of gate oxide layer, and definitely when we vary the thickness of gate oxide layer, so it will make a huge effect in the different parameters of MOSFET and the different parameters of transistor. Okay, in the defect free, it is already mentioned that in the defect free gate oxide, the electric field value is limited to 7 to 8 millivolt per centimeter. It is for a 20-year lifetime at a 125 degree centigrade. Okay, but in the case of defects, the electric field value in the gate oxide layer will be limited to 4 millivolt per centimeter. It is mentioned here. Okay, what is it mean? It means that the thickness of gate oxide layer, or we can say the scaling of gate oxide layer, plays a very vital role, plays a very dominant role in the case of optimization of technology, in the case of technology variation. Okay, with the variation of gate oxide length, the other parameter will also vary. When we vary the thickness of gate oxide layer, when we vary the size of length of gate oxide layer, in that case the other parameter value, the value of other parameters will also vary. The variation of other parameters, when we vary the gate oxide length, is represented in this table. This table is for inverter circuit. We make an inverter circuit. We made an inverter circuit by using PMOS and NMOS. When we make a CMOS circuit, there PMOS is act as a pull up resistor, and NMOS is act as a pull down resistor. But the current carrying capacity of PMOS is just half as compared to NMOS. When we attach PMOS and NMOS and make a CMOS circuit, so in that case the variation of gate oxide definitely vary the other parameters such as VDD, VT, TOX, saturation current, etc. So for the inverter circuit, some variation is represented here. The change of drain saturation current in the NMOS is represented with the change in technology. Change in technology. All is represented here. Okay, so this one is all about the effect of scaling. These parameters, which is changed due to the change in gate oxide length. Also, one more comparison table is given here. When we minimize the electric field, or when we minimize the duration between two gate pulses, at that time what will be the effect in VDD, TOX, W by N ratio. Now, what is the mean of W by N ratio? W by L ratio means the width and length of any width and length of any oxide layer in any MOSFET. Suppose if I am taking a PMOS, so definitely we use a gate oxide layer, and in that gate oxide layer some thickness is there, some length is there. So when we divide the width and the length of that particular gate oxide layer, so by using that we will get the ratio of W by L. So this W by L ratio is the important parameter when we represent any technology scaling. Here WP upon WN, it means that the oxide width of PMOS and the oxide width of NMOS. So this all variation, this all parameter variation is represented in this table, and also with the variation of gate length, the variation of other parameter is represented here. Okay, so this one is all about, the impact of technology scaling. Okay, so this one is all about the impact of technology scaling. Okay, here one graph is represented here. This is mentioned with respect to technology generation. What is the mean of technology generation? Technology generation means the length of gate oxide layer from drain to source. So here, if 2 micrometer represent the gate oxide length, 1 micrometer also represent the gate oxide length. So this axis is all about the gate oxide length, and we will consider it in the for the NMOS transistor. So this one, the variation and the high speed is represented by using these graphs. Okay, so this and the below mentioned graph represent the gate delay along with respect to the gate generation, along with the respect of technology generation. Technology generation means the with the changes in gate oxide layer, what will be the effect on gate delay? It is represented in the second graph. Okay, now the second topic is technology and device innovation. Now the second topic is technology and device innovation. Okay, many high-speed devices are proposed, such as quantum tunneling, single electron, single electron, and also on the basis of motion of atoms. Okay, so on the basis of these various technologies, various devices are proposed to speed up the device, or to minimize the power dissipation. These all device technologies are used. These are good, but they are not capable to drive the capacitance of long interconnection. Okay, these technologies are not able when the capacitance, when the connection between when the interconnection between the two elements are very high. So at that time some capacitance is produces, and these technologies are not capable to drive these capacitance. So definitely in that time of manufacturing, it is a major challenge. Okay, so in that time, in the case of manufacturing, it is a major challenge for the manufacturer. Along with that, the circuit architecture is not suitable with this design technology. Okay, the circuit architecture is not suitable with this design technology. So first what we have to do, what the designer have to do, the designer first implement a circuit architecture, and after making circuit architecture, they can implement their own device technology. Okay, so it is better to first find the low power architecture, then develop the various device technology according to that circuit architecture. Okay, so this all are mentioned in the first paragraph. Now if we discuss on the basis of material that we use for making a semiconductor, so in the case of GAS, germanium arsenide, so in the case of GAS, speed power benefit is not sufficient. In the case of GaAs, gallium arsenide semiconductor, the speed power benefit is not sufficient as compared to if we make a semiconductor by using the silicon only. Okay, so it means that this SOI, what is the mean of SOI? SOI means silicon on insulator. What is it means? It means that silicon on oscillation insulator. So this silicon on insulator technology can improve delay and power through a 25% reduction in total capacitance. Okay, and we know that when the capacitance is reduced, so definitely when the capacitance is reduced, so definitely the power will reduced, because the power is directly proportional, power dissipation is directly proportional to capacitance. We already discussed it in our previous lecture that the power dissipation is of two types: dynamic and static. And dynamic capacitance, dynamic power dissipation is represented by VDD C, VDD square, VDD square into C. Okay, it means that the capacitance also play an important role when we discuss about the power dissipation, when we want to minimize the power dissipation. So if we use the silicon on insulator technology, so at that time the power the total power will decreased up to 25%. Okay, so in this SOI technology, this capacitance is reduced because we use wafer bonding in SOI. Because we use wafer bonding in SOI. Okay. Now, what is the mean of wafer bonding? What is the mean of wafer bonding? In wafer bonding, two bulk silicon wafers are oxidized, and two oxide surfaces are holded together and bonded at a very high temperature. Why it all done? Because to minimize the oxide capacitance. So in these two wafers, one is thinned by polishing, how can we polish then thin oxide layer? We can polish these oxide layer by using the plasma or chemical etching. So in these two wafers, one is thinned by, or we can say one is polished by chemical etching until its width will reach 2000 angstrom. Until its width will reach 2000 angstrom, uh, the designer will polish the wafer, so that the optimized SOI MOSFET can have lower capacitance and slightly higher drain saturation current than bulk devices because of reduced body charge and small threshold voltage. Okay, I am repeating it again. The optimized SOI MOSFET can have lower capacitance and slightly higher drain saturation current than bulk devices because of reduced body charge and small threshold voltage. Okay, so this will provide the improvement of approximately 40% in speed. Okay, so another way, there are several ways to reducing the capacitance. Another way to reduce this capacitance is to use the minimum possible width of metal interconnection. Now, where we use this metal interconnection is used when we want to join two layers. Okay, so these layers are made with metals, and when we want these two layers, so at that time, or we can say when we want to extract the internal extract the when we want to connect the outer atmosphere with the internal atmosphere with the internal circuitry of the circuit, so at that time we use some metal contact. So in that time of metal interconnection, when we use metal interconnection, so it definitely produces some capacitance. So one another way to reducing the capacitance is to reduce this metal interconnect. Okay, so according to recent research, it is found that the AC interconnect can carry a many times higher current density than designing rule based DC interconnect. Okay, this is due to the self heating effect. This all will done due to self heating effect. Okay, so another way to reduce this capacitance is to use the low permittivity insulator, low permittivity inductor. Okay, it is also mentioned here. So at last, to minimize this power dissipation, or we can say to speed up the process, uh, out of various device technology, we can use one of them, such as DTMOS. One is DTMOS. DTMOS is dynamic threshold metal oxide semiconductor, because this dynamic threshold metal oxide semiconductor is very low power voltage, is very is this technology will produce a MOSFET that dissipate very low power. Also, the speed of these devices are very high. Okay, so in this DTMOS, the VDD voltage is generally in the range of 0.5 volt, and when we use the VDD voltage as 0.5 volt, so in that case the threshold voltage is limited, less than 0.15 volt. Okay, it is all represented here. So DTMOS demonstrate that a MOSFET can have higher threshold voltage at gate voltage equals to 0, at gate voltage equals to 0 for low leakage current, and also a low threshold voltage when gate voltage is equals to supply voltage VDD for high speed. Okay, or we can say in any time the threshold voltage may be the threshold voltage will be the function of gate voltage, will be the function of gate voltage. So this one is all about the innovation part. So this one is all about the device innovation part and technology. So I hope all of you understand these two topics. So thank you so much. In next class we will discuss some other topic. Thank you so much.